This is an introduction to the Freescale Semiconductor Very Low Power 16-bit Digital Signal Controllers. Welcome to the training module on the Very Low Power 16-bit Digital Signal Controllers. This training module gives a brief introduction to its features, target applications, its peripherals, and block diagrams of a few applications. The MC56F8006 and the MC56F8002 series combine on a single chip the processing power of a digital signal processor and the functionality of a microcontroller unit with a flexible set of peripherals to create an extremely cost-effective solution. This device uses the 56800E core, which is based on a dual Harvard-style architecture consisting of 3 execution units operating in parallel. This allows as many as 6 operations per instruction cycle. A full set of programmable peripherals support various applications. Any signal pin associated with these peripherals can also be used for general-purpose input/output GPIO. Power-saving features include an extremely low power mode and the ability to shut down each peripheral independently. Here we explain about the applications of this device. The MC56F8006 family is aimed at power and cost-sensitive motor control applications such as 3-phase BLDC motors, variable frequency drives, permanent magnet synchronous motors, and handheld tool motors. In addition to motor control, targeting segments for these devices include board-mounted digital power supplies for servers, industrial and telecom power supplies, smart power metering, and advanced lighting control in commercial buildings and factories. This page shows a block diagram of the device and illustrates how the 56800E system buses communicate with internal memories and the IP bus interface and the internal connections among each unit of the 56800E core. The 56800E core is based on a dual Harvard-style architecture consisting of 3 execution units operating in parallel, allowing as many as 6 operations per instruction cycle. The MCU-style programming model and optimized instruction set allows straightforward generation of efficient, compact DSP and control code. The instruction set is also highly efficient for C compilers to enable rapid development of optimized control applications. The new Freescale MC56F8006 DSC family boasts a standard current of less than 1 microamp. Also, with the core operating at 32 MHz and the peripheral clock at a maximum of 96 MHz with all peripherals running, the Freescale MC56F8006 draws just 50 milliamps, which is very competitive compared to other devices with similar math processing abilities. This page gives you the DSC attributes. The multiply accumulation MAC operation is the fundamental operation used in the DSP. The core of the MC56F8006 series has a dual Harvard architecture optimized for MAC operations. The 2 operands, C and X, are directed to a multiply operation and the result is summed. This process is built into the chip by allowing 2 separate data memory accesses to feed a single cycle MAC. The entire process must occur under program control to direct the correct operands to the multiplier and save the accumulated result as needed. Because the memory and the MAC are independent, the DSC can perform 2 memory moves, a multiply and an accumulate, and 2 address updates in a single operation cycle. As a result, the DSP and MCU benchmarks execute very efficiently. This page gives the advantages of the DSC features. They are intended to reduce the cost and complexity of digital power conversion applications, such as board-mounted digital power supplies in servers, industrial and telecom power supplies, and smart power metering. The MC56F8006 has powerful signal processing capabilities which can be applied to advanced lighting control in commercial buildings and factories. The ADC can perform an analog to digital conversion on any of the software selectable channels. In 12-bit and 10-bit mode, the selected channel voltage is converted into a 12-bit digital result. In 8-bit mode, the selected channel voltage is converted into a 9-bit digital result. When the conversion is completed, the result is placed in the data register. In 10-bit mode, the result is rounded to 10 bits and placed in the data register. In 8-bit mode, the result is rounded to 8 bits and placed in the ADCR register. The conversion complete flag, COCO, is then set, and an interrupt is generated if the conversion complete interrupt has been enabled. The Programmable Gain Amplifier, or PGA, is intended to operate in conjunction with the on-chip analog-to-digital converter. By itself, the PGA has no useful function, but when used to pre-process ADC inputs, it amplifies and converts differential signals to a single-ended value, which is passed on to the ADC for conversion to digital format. The PGA differential amplifier is a switched capacitor circuit that amplifies a differential input signal and converts it to a single-ended output. The high-speed comparator module, HSCMP, provides a circuit for comparing two analog input voltages. The comparator circuit is designed to operate across the full range of the supply voltage rail-to-rail operation. The HSCMP module is capable of generating an interrupt on either the rising or falling edge of the comparator output or both. The interrupt request is asserted when both CMP0_SCR bit and the CMP0_SCR CFR are set. This module provides the 2-time system clock frequency to the System Integration Module, SIM, which it uses to generate the various chip clocks. The on-chip clock synthesis module allows product design using an internal relaxation oscillator to run the device at user-selectable frequencies up to 32 MHz bus clock. The on-chip clock synthesis OCCS module interfaces to the oscillator and phase lock loop. This device has more options for clock generation than do the other members of the MC56F8000 family. The SIM is a system catch-all for the glue logic that ties together the system on chip. It controls distribution of resets and clocks and provides a number of control features. The OCCS configuration controls the operating frequency of the SIM master clocks. In the OCCS, either an external clock, a crystal oscillator, or the relaxation oscillator can be selected as the master clock source. An external clock can be operated at any frequency up to 64 MHz. The crystal oscillator can only be operated at 8 MHz. The SIM uses master clocks from the OCCS module to produce the peripheral and system DSC core and memory clocks. A 3 times master clock input from the OCCS operates at 3 times the system and peripheral bus rate, and therefore at a maximum of 96 MHz. The Computer Operating Properly COP module is used to help software recover from runaway code. The COP is a free-running down counter that, once enabled, is designed to generate a reset upon reaching 0. Software must periodically service the COP in order to reload the counter and prevent a reset. The COP sits on the unswitched digital supply and can continue operation while the SoC is in partial power down mode. When the COP is enabled, each positive edge of the prescaled clock causes the counter to decrement by 1. If the count reaches a value of 0, then the chip is reset. Here we show the JTAG block diagram. The JTAG port has 4 read-write registers: the instruction register, the chip identification register, the bypass register, and the boundary scan register. The master tap consists of synchronous, finite 16-bit state machine, an 8-bit instruction register, a bypass register, and an identification code register. This device has a 56800E core containing its own test access port, or core tap. A tap linking module, TLM, is included to manage the tap access. Normal operation of this part will use the chip tap as the master tap controller, thereby disabling the 56800E core tap controller. The tap controller is a simple state machine used to sequence the JTAG port through its various operations. The JTAG port supervises the shifting of data into and out of the EON-CE module through the TDI and TDO pins. This page shows a portable battery-powered pulse oximeter, a medical device that indirectly measures the oxygen saturation of a patient's blood. The MC56F8006 and MC56F8002 controls the device. This application requires low power standby mode and dynamic operation frequency to extend battery life. The high-speed timer module helps to sample in real time the 2 wavelengths digital light signal pulses that pass through the detector. Here we illustrate the use of the comparator sampling mode for sensorless BLDC applications. In this application, comparators detect the zero crossing of back EMF generated in a motor's winding. To avoid false zero crossing detection due to noise or changes of back EMF reference, synchronize the PWM pulse and the comparator output. In this case, the comparator can be programmed to send its output to the CPU when the comparator comparing window is open, which is triggered by the PWM module. Here we show an application block diagram of a 3-phase BLDC motor. It uses the features of its on-chip peripherals like 3 high-speed comparators, dual 12-bit analog-to-digital controllers, 2 programmable gain amplifiers, and a pulse width modulation with up to 6 outputs. The PGAs operate in concert with the ADCs to amplify small signals, increasing the ADC input dynamic range. The PGAs also perform differential to single-ended conversion of analog signals. The pulse width modulators enable power conversion functionality and accuracy for digital power supply and motor control applications. Multiple system faults are detected and processed by onboard hardware to immediately shut down the PWMs in the event of a threatening or dangerous situation.